everyone. Welcome to NSTA Web Seminars, where you can find live interactive learning at your desktop. My name is Paul Tingler. I am the Director of Web Seminars at NSTA, and I'll be moderating tonight's program. Presentation tonight is part of the NASA Explore School series, and it's entitled Engineering, Design, Forces, and Motion, the Great Boomerang Challenge. Our presenter is Rudo Kashiri. Welcome, Rudo.
Thank you, Paul, and welcome everybody tonight. And also, hopefully you will get something tonight that you can use with your classes. This is, like Paul said, for middle high school, but I have found that some younger teachers for younger grades have also used this lesson as well. Now, before I start, I'd like to find out how many of you are with us that are with NASA Explore Schools. If you would just show me with a green check. Okay, I noticed quite a few. Numbers are getting larger and larger every day. Very good. Now, the reason I'm asking is I want to remind you to go to the virtual campus, go to the lesson library, and you need to look for the survey for this lesson today so you can log your participation. And those who are not NES educators, you will find information at the end of the presentation. I will go over more information if you need also after the session if you want to find out how you can join NES. So the first thing we're going to do is I'm going to go ahead and start with our agenda. We're going to start with the lesson overview. And then I will talk to you a little bit about the NASA connection to this lesson. As we do most of our NES lessons, we always show you a NASA connection, so you have a way to talk to your students about how to connect what you're teaching to NASA. And then a little bit about STEM connection, because this lesson can be a lot of fun for students, but I also want you to be able to connect it to what you're teaching in your class, so you can your students can get something out of it to connect what you're doing in the classroom. And then there are a few extensions and resources, and then we'll talk about NASA Explore Schools at the end. So we've got a lot on our agenda tonight. So the first thing is, like I said earlier, the lesson is for grades 9 to 12, but you're going to find out there are ways that you can use the lesson. And also I have a link that I'm going to give you in just a little bit on how you can do the same lesson with the younger students. Somebody joined us last time, teaches 4th or 5th grade, and they wanted to do the same lesson, and I found a great lesson they can use that's a little bit easier, and you would still be able to accomplish most of the goals that we're going over today. And then the next thing is the subject areas are science and engineering. So if you're looking for a good engineering design lesson, this is a good one, and also connecting to the science concepts that you're teaching in your class. Hopefully you'll be able to find some of that from the lesson today. And then the national standards that we're covering today are from physical science, your forces in motion, and from science and technology, we're going to look at abilities of technological design, and then understanding about science and technology. And then the prep time for this lesson probably take you about 30 minutes. The most time is going to come from you setting up a place where the students are going to be having the test flight. Now, you could actually do this lesson indoors if you have an area in the gym or cafeteria that you can mark. You can do a lesson indoors, or you can go outside and actually mark on a field or a basketball court. So depending on your situation at your school, and so you can figure out which one works better for you. Now the class time will take you probably as much as 3 50-minute periods. Some people have taken longer. Now some teachers found out that students really got into it and they did a lot more designing, so it might take you a little bit longer. Or some of you probably find some ways that you can cut the lesson, especially those who have older students, so it might not take you quite as well. But count on a good 3 50-minute periods. Now the lesson is, the objectives are to use the engineering design process to complete a team challenge. So your students are going to be working in groups, and also to show how aerodynamics forces influence flight characteristics of designs. And we're going to look closely at Bernoulli's principle. Now, another great thing also, the lesson has all the information that you need, the objectives and some background information. And for those of you who are NES Expert Schools educators, you'll be able to find information on the virtual campus. And for those who are not, what I did is in the chat, I am going to let you look at a couple of things. The first thing, that the link is for the guide. So that'll be where you can find the guide if you're not a NES Expert School educator. And also there's a design packet that I'm going to talk about in just a second. So you have two things coming out in the chat window right now. So this is what the lesson guide will look like. Now, in addition to the lesson guide, you're going to need a packet design. And all the packet design is, it has the engineering design challenge on there. So you actually have some kind of idea of what the steps that your students will be going through. And as the students are going through the steps, there are handouts that they will be actually writing. Like when they're brainstorming ideas, they write out what they came up with. And then when they start building, they're going to also be writing everything that they're doing. So you have the packets ready for you. And that's the second link that I send you. And then the other thing that's also with the lesson is there's a rubric that you're going to need, and so that's also part of that. So the engineering design packet that you will need for this lesson will say middle and high school. Now, if you teach elementary students, if you go to the same area, you will find the engineering design packet for your younger grades. And you can use the same thing as well. Now, like I said earlier, some of you are going to be using this lesson. I saw, I think, 3 people, if I remember, that have younger students. Now, if you're one of those people, what you need to do is you can actually download the link that I just put on there right now has the lesson for the younger kids. And all it is using manila folders and a pair of scissors and making it a lot easier for your students. So you can check it out if you have younger students. Now, for everybody else, I would like for you to go to that link as well, because there's a template that is mentioned in the lesson, and I didn't find it anywhere in the lesson. So, so we're killing 2 birds with 1 stone right here with this link here. So you can get the elementary students lesson, and also you can use the template that's there. So those are the main things that you're going to need. Now, before we get into our lesson about boomerangs, I just have a question for you. Now, if you have, I know if you came in a little bit later, maybe you did not hear when Paula said this, should you wear the check-in XR? I'm going to give it to you, Paul, so you can do the polling question.
Thank you, Rudo. And you can find the poll voting button still up underneath your name and the word participant. In the last button there, you'll see now a check in the box there, as we have a check in X, the check for the true, and X for false. So please go ahead, if you haven't already done so, and vote now. And I see most people have found the voting, and I will let you turn it back to you, Rudo, to respond to them while I display the results.
All right, thank you. I see 28 of you are saying true and 4 are saying false. Now, before I answer this question, Paul, I have that video, the very first one. What is it, Boomerang? I'm going to have you play that one for me, and then we will get our answer to the question. And if you still did not get the video, then I will give you the answer at the end. I'm going to hold on this answer for just a second. Just remember, some of you said true, and some of you said false. Oh, by the way, you might want to turn down your volume for it, because it's going to come up really loud.
Hi guys, my name is Gary Broadbent, a member of the United States World Championship Boomerang
Okay, so from your answers, the correct answer is false. So if you did not get it, he did talk about boomerang was never used as a weapon. There is something called a Kylie, and Kylie is spelled K-Y-L-I-E, and that's what was used a long time ago as a weapon because it was meant to go and hit the target, but a boomerang is actually meant to come back. Now, I only showed you like a couple minutes of this video. If those of you who are NES educators, you will be able to find a lot more information about Gary. He is like one of the boomerang champions, and he does a lot of boomerangs. Actually, he actually quit his job, and he does go around different areas in the Cleveland area talking about boomerangs to different groups. So and he does really good because he talks a lot about the science behind how it works, and as well as the competition that he does. So if you get a chance to see it, it is really, really good. And those of you who did not, hopefully you can bookmark the link and look at it a later time. In these videos, I noticed they're opening up an extra window, so some of you are still looking on the screen and could hear something but could not see it. Maybe that's what the problem was. But anyway, so does he speak to schools? Yes, he does, but he's from Cleveland, so he kind of goes around those schools in those areas more than any others. I don't know if he'll go out of town or anything like that. So if you're in the Cleveland area, just look up his website, and maybe you can find out how to sign up for him. But he's really cool. I mean, he talks a lot about boomerangs. I learned a lot from him. When I started this lesson, I had very little knowledge on boomerangs, so he's really good at that. So anyway, did anybody have any questions? I noticed that we had one from Barbara. Hopefully that was it. And Paul, if I miss any, I'm going to give it to you.
Thank you, Rudo. And I did not see another one other than Barbara's question down there. So if you do have questions, please go ahead and type those in the chat at this time. And if you typed a question previously and we don't happen to catch it, please go ahead and bring that back when we do stop for questions, as that is our opportunity to pay attention more closely to those, as there is quite a bit of information that goes back and forth in the chat, and that's great. But if you have a question, go ahead and drop it there now. And I see a question from Michael there about, is the video available at NES? Rudo?
It is. And when you go to NES, you're going to find out the longer video of Gary, because he actually throws it and talks a little bit more about it. I was trying only to make it as short as I can, and also get you to see what boomerangs are for those who did not have that information. So if you go on the NES website, you're going to find out more about it. If they say, do all boomerangs work? Well, you're going to find out that some of your students will have some that do not work, and this is part of the design. And the students that we work with, some of the students did not get theirs to work, but after they found out what others did, they were able to go back and redo theirs and get it working. April says the video going to be available in the webinar archives. For this webinar, all you're going to get is this 2 minutes of the video. And like I said, that's the only length I could get to you guys to get it to play without taking too long. Depends on what you, okay? All right, so somebody said it depends on what you mean by working. Okay, the idea is coming back to you. If it comes back to you, then it's working. All right, so what we're going to do is get into the lesson in detail. So the Boomerang Design Challenge, your students are going to design a returning boomerang, and that we allow the greatest flight distance relative to the accuracy of the boomerang return. Okay, so what we'll do is the material that you will need. Remember, I told you you're going to need a template. That's what this little template is, and there was no way in the guide. That's why I gave you that link so you can look at it. And then, of course, you're going to need your handouts. And one other thing that's really important for this one, those sheets of craft foam. And this is where it's going to be really hard for the younger kids to cut, because this class was actually using X-Acto knives, if you look in this video, in this picture, and scissors, which is going to be too much for the younger students. And so if you use manila folders, then it'll be okay for you to cut it with the scissors. And then they use, they have some cardstock and also some hard construction paper, and the students actually use index cards and cardstock in addition to the craft form, because remember they had to make the leading edge and the a certain way to make sure they're working the aerodynamics there. So they use pretty much everything that we gave them. So index cards are part of that too. And then they use the middle duct tape. Middle duct tape is a little bit heavier, so your students will be able to use that also in the areas where they want to add a little more weight. And then, of course, you got your regular duct tape and some glue and markers and scissors. And what we use the string for is you will stretch your string maybe every meter, make a little mark on the string, so you're not worried about going around trying to stretch your tape measures and try to figure out how long you're going to make it. So that's what the string is for. So when you go outside, and of course you're going to need your timer because you're going to try to figure out how long it takes for the boomerang to stay in the air. And once again, the lesson gives you materials, but you can also add your own materials. This is just some of the basic stuff that you can use. The craft foam worked really well for the older students, and some of the older students realized that they did not need a template after they started designing there, so that's going to be up to your class. And so they just decided to do their own designs. As you saw, Gary had all kinds of shapes for boomerangs, so that's something that you can work with your students. And once again, that's where the engineering comes in, and you'll be surprised the ideas that your students come up with. So this lesson follows the 5E inquiry lesson design. We're going to talk about you engage, explore, explain, extend, and evaluate. So as you're going through the lesson, I'm going to kind of share with you how each one of them plays a role in the lesson. The first thing is the engage part. You want your students to know about aerodynamic lift. And so that's what the teachers do in this particular class, finding out from students what they know about lift. And he found out from this class that they really had that much knowledge, even though it was a high school class. And so he went through talking about how airplanes fly and the shape of an airplane, so the students had a better understanding of what aerodynamic lift is. So that's what you want to do with the engage part of the lesson. And then the next thing that you want to do is explore. Now, when we work with the students, this is the part that took the most time because the students were actually going to design, and they're going to build, and then test the models. So this is where most of that comes in. And so the students really took a long time because they really were concerned about their designs being aerodynamic before they even went out. And then they started cutting, and the cutting part also took quite a bit. And then the testing was a lot of fun for the students, and especially for those who were successful the first time. And so what I'm going to do is just go through the engineering process, because as the students were doing the as you go through the 5 E's, you will notice that it's pretty much kind of like the same thing as you do with the design challenge. So the students started by designing their modules, their boomerangs, and then they built them, and then they got to testing them, and then they were recording that data, and they were able to analyze their data, coming back in the classroom and discussing their data, and then some of them actually wanted to go back and redesign and test them again. So what I'm going to do, Paul, we do have a second video. And what we're going to do, play that one. And remember, the video might play on the separate browser on your computer for those who are not getting it the first time. And just let you see how the teacher got the students outside and getting ready for the flight testing. Okay, so that was the classroom, and as you can see, the students did have some fun outside, and somebody was asking, was there any research done of boomerangs before that? For this particular class, no, and the reason is because we were trying to get the videotaping in a certain period of time, but the lesson does recommend that you actually do the testing. I mean, do the research on some of those terms with your class before you start. And what we did with this classroom, we recommended the teacher to give the students vocabulary words that we thought they're going to be running into as they do their explaining, because they really did not have time to do the research. But this could be something that you will need to do, and it is also recommended to read that. And also, I'm going to talk about one of the Boomerang champions, Ted Bailey. He's also mentioned in the lesson, and they asked the students to look more into what he did. So there is some research. All right, and I don't know if I missed any other questions. I only saw that one. If anybody else does, Paul, if you saw any, let me know. I'm going to stop for a second.
Thank you, Rudo. And I didn't think I saw any other questions other than the one by Therese there. So if I see a couple people typing those, so we'll give them a moment to do so, and go ahead and ask your questions now if you have them, and I'll turn it back to you, Rudo.
Okay, I think you're still finding about where do you find the materials. A lot of the stuff that you saw were what you find most of the time, but the craft stores will have the craft form, if that's what you're asking for. Metal duct tape, the regular stores would have also your have the metal duct tape. I think those are the two that might be harder to find, but as far as everything else, you will be able to find it just about everywhere. And like somebody had put on there, you can find use recyclable materials. So your hardware stores will have the metal duct tape, and the craft stores would have your craft form. I don't know if that's what you're asking in your question. And I do not see any others. And I think Teresa is still asking about is the video on the, yes. Actually, on the NES website, you're going to find the full class videos, and you'll find, I only showed you this one. The class actually comes back, and they talk about what they found out, which is going to be our next stage, explaining. And I'm not going to show you that video today, but you'll be able to find that. And then I'm going to be hitting all the other videos that you'll be able to find as well. So when you go, you'll know what to look for. All right, so that's it. Oh, I didn't see if I have any more before I move on. I think that was right. Okay, thank you, Stacy. It's called foam core. Okay. In the lesson, they call it craft form, so I didn't know. Thank you. All right, so the next part is explaining. And once again, there is a video on the students actually come back in class, and they're talking about what they found. And the key to explaining, this is where you want your students to start bringing up some of those terms that they learned as the boomerang was flying. So your vocabulary is going to depend on the level of your students, and also it's going to depend on what you're teaching. Whatever concepts you want to come across is going to be what you direct your students to use as they do their explaining. So that's kind of what happened here. And then the next thing is I'm going to ask you a question first before I move on to the next thing. Will a boomerang work in microgravity? Okay.
Once again, go ahead and use the poll voting buttons up there underneath your name under the word participants, and the last button there is the check right now, and you can choose either the check or the X to determine whether or not the boomerang will work in microgravity. And go ahead, if you haven't voted now, please do vote. Go ahead and guess if you want. Again, it's a blind poll, and we'd like to see everybody respond.
Okay, great. I'm seeing a lot of yeses and yes. And once again, there is actually a video of the Japanese astronaut Takao Doi. He actually did the boomerang, and it's really cool. You actually see him throwing the boomerang, and it's going to be coming back to him. So that's another great one that you can look at. Now, and plus, those of you who are understanding, well, microgravity is that strange environment that astronauts experience when they're in space. You know how they're floating around? A lot of people call it zero gravity, but we want our students to know that the correct term is microgravity, because when you think about it, even though they're so far away, maybe 300 kilometers away from out in space, gravity still exerts about 90% the attractive force of the Earth's surface. So they're still getting some. So we want to say it is microgravity. There's some gravity and not quite as close to what we have at Earth. And a lot of people just refer to zero gravity. But anyway, that's what I was talking about. But if you were to take the same boomerang outside the space shuttle, would it work? Let's see if somebody will put an answer in the chat for us. In the vacuum of space, will a boomerang work? In a vacuum of space, will the boomerang work? I'm going to see if somebody put the answer in the chat area for us. So these are some of the things you might want to bring up with your students. And also the lesson recommends that as the students come back, they're going to compare what they learned to what they know how their boomerang worked, to compare it to what it will do in microgravity or what will do in a vacuum. Of course, they know it's going to need some kind of air. So if you're in a vacuum, then it's not going to work, right? Like Michael said, you're going to need the lift. All right. So anyway, so that's what that is. And like I said, there is a video on microgravity and the boomerang. As you can see, this is the little picture of Takoa doing the boomerang experiment on the ISS. All right. And then the next thing is evaluate. Remember I showed you earlier the rubric? You can pull that out and let the students look at that and use assessment. You can assess your students' learning that way. And the next thing that I'm going to do is I'm going to lead you into, let me see, do I have any questions? I'm going to pause for questions, but while I'm doing that, I have a link that's going to take you guys to a simulator that we're going to look at. So what I want you to do is if you go ahead and click on that, the link that I just put in the chat, and I want you to make sure you open that browser and keep it on the side while I'm going. For some people, it might take a few minutes to load, and that's what I'm giving you to now. Don't do anything with it yet. I'm just giving you time to make sure that you have, make sure you get it loaded on your computer. All right, so go ahead and click on it and get it, and once you do it, just put it on the side, and then get back to where I am. And Stacy just gave you a link to the International Toys in Space. That's another one also where you can find it. And some of you who use NASA Eclipse videos, you can find the Eclipse video that talks about the microgravity experiment, showing you him actually doing the experiment. So those two are a little bit different, the Toys in Space and the one that I'm talking about. All right, cool. So go ahead and click on that. And in the meantime, we're going to move on to the next section where we're going to talk about the NASA connection. Let me see. Boomerang template will... Oh, okay. I thought I was a question on there from Stacy. But anyway, so they do have the template on that particular one. Yes, correct. The next thing that we're going to do is look at the NASA connection to this lesson. And one of the things that you want to do is just to make sure that your students understand what's going on. You want to give them more information about what is going on with the lesson and also how they can connect it to what you're actually teaching in your classroom. So for those of you who remember the first A in NASA, that stands for aeronautics. And a lot of people think about NASA and forget about the aeronautics part. Everybody thinks about going to space. But that's something that you might want to introduce to your students. And also they need to know that NASA uses a lot of wind tunnels to learn more about flight characteristics. And they're designing a lot of new aircraft, and to make any designs, any modifications, they do all of that in the wind tunnels. So aerodynamic research, engineering studies, and computer simulations, they've all led to design changes that have increased the boomerang performance. Now, before I looked at this lesson, I didn't even realize that there was actually boomerang competition was actually an international event. But then your students will know that with the, this information, new boomerangs are now staying in the air longer. So drawing upon existing NASA low-speed aircraft research, designers have actually used computers to alter airflow sections to their boomerangs to make sure that they have they maximize the lift and also minimizing the drag. So that's something that you might want to be emphasizing to your students. So performance improvements have led to creation of the International Boomerang Challenge. Now, some of your students might not even know that it does exist. And so scientists have been doing a lot with it, and they found out that these boomerang competitions, they're looking at different things like accuracy, they're looking at distance, catching, and there are also some people who actually do two boomerang juggling. And of course, the common one is maximum time of aloft. So they are looking at all those things. So boomerang competition designers are applying aerospace technology from basic aerodynamic computerized flight simulations, and we're going to try to look at one today. Now, I also told you earlier that your students will learn about one of the boomerang champions named Ted Bailey. Now, he's like one of those highly ranked boomerang designers and also a thrower. And what he did is he did look at a variety of NASA technical reports on aerodynamics and low-speed airfoils. And so that's how where he got his information to design his competitive boomerangs. So your students can also probably do a boomerang challenge in your class. Once they make their designs, they can go back and do their own boomerang challenges in your class. So hopefully that's something that you will be able to do as well. Now, another cool example of what's going on with aerodynamic research is the X-48. Once again, for NASA Explorer Schools educators, we have one of our NASA Now classroom videos. They talk about this X-48B aircraft. And as you can see, this is like one of those very cool aircraft. When they, this is just a small representation of it. Actually, you're seeing a 8.5% scale of the full model. Now, the full model is expected to have a wingspan of about 200 foot and also weigh almost 1 million pounds. So you're talking about a large aircraft. Now, it is really cool because it doesn't have a really distinctive fuselage or wing. It's kind of like a combination of both. And what they're doing right now is they're actually studying it. Where I work, they actually have models where they are testing in the wind tunnels and to see how the air flows over the wings and under the wings, and trying to figure out the best way to like I said earlier, to make sure it flies better and check out the aerodynamics that they need for this type of aircraft. So this could be something that you can get into, and like I say, there is a whole NASA Now classroom video on this, and so you can find out more information about the X-48B. Now, what we're going to do is, I'm hoping by now everybody has had a chance to pull out the simulator. Now, what I would like to do is, if you have the simulator now, if you would just give me a green check, and that will let me know when it's time to go. Now, because we're trying to do this together, it'll help if we all stay on the same place. So if I can have a green check from everybody who has their simulator already. If yours is not coming up, what I've done before is I just close it and come back, and then it'll pop up. And what you do is, if you're not seeing, just move down. It's going to be halfway down the page if you're not seeing the simulator. And it's going to look like the page that I have on the whiteboard right now. So I'm only seeing 16 people out of 48. I'm trying to figure out what's happening with everybody else. Please give me a green check if your simulator has opened up and you're seeing something that like I have on the screen without the red and the yellow colors that you're seeing on here. And I'll tell you why I have those arrows on there to help you. I need to see, I'm going to have 21 out of 45 now, and only one person is saying no. So some other people are not responding to me. Corbin, I don't know. Oh, please send the link again. Okay. We can do that. If you did not get it, there's the link again. Okay. I can see. Okay, great. All right. I've got more than 24 people. I'm only seeing 24 on there with the check, and some other people are not voting. Now, remember, you got to work with me, because if you fall behind, then you're going to be behind. Since I cannot see what you're doing, I have no idea. Ty, if you let me know what your issue is, and maybe we can work it out or see what's going on. Everybody good? I only got 24 out of 45. That's still a lot of people not responding. Let's go. Okay. All right, because I don't want you to get lost behind, because once you do that, then it's going to be hard. Okay, while they're getting there, we're up to 30. Great. Now, the things that I want you to look at, if you would just look on the screen and then kind of compare to what you have. Now, you're not going to see the A and the B on your simulator, but I put on there just to give you an idea of what I want you to do. So the first thing is, where the top of the A, we're going to move a probe there, and the probe is this little purple dot at the end of that airfoil, and I've labeled probe so you can see where it's at. And the way we move that probe, if you would move and look to the right with me, right there where it says probe on the right is what we're going to use to move the probe. Let me click on that, okay? So you're going to move that little blue button to the left, and that will move the probe for you, okay? And what I want you to do is you're going to move it to the tip of where this arrow is labeled A. And once you do that, you're going to see a reading of velocity on the right side of your simulator. I'm going to go through these directions again. I'm just trying to get time here while I'm getting everybody get caught up. All right? And then once we're finished with that, we're going to move the little probe up to where B is, at the tip of B. And the way you do that is pushing up, where it says probe up, that little blue button, you're going to use that to push up, and it will go up. Okay? And then the other thing that I want you to look at are, you're going to see where we change the angle. At some point, I'm going to ask you to change the angle. The angle is going to be right there where we change with the, represented by the blue. And the lift is represented by this blue arrow right here. Okay? Now I'm up to 30. I'm waiting for those people who have not told me they have a simulator yet. If you have not, please do that. I'm checking the numbers. Okay, so the first thing that you're going to do, everybody who has a simulator, I want you to push onto the velocity button, push that one in, okay? And then you're going to push the animation button, and you're going to push the close view. If you would do that on your simulator for me right now. Okay, I'm up to 31. Okay, good. Michael's saying done. I'm going to go with you, Michael. All right, so we're going to move on to the next thing. Now, so what I want you to do, the experiment is, with your airfoil set at 0.0 degrees, make sure it's set at 0, 0, okay? I want you to push the probe, I want you to push the velocity, animation, and close view buttons. I showed you where those are. Go ahead and do that for me. And then the next thing I want you to do is to move the probe to the point, or the arrow point where A is, so we can read the velocity. And what I want you to do is, once you know the velocity, please put it in the chat area for me, and that's the only way that I know that you guys are with me. Tell me what your velocity is for point A. Okay, great, great, great. I'm seeing numbers. All right. The rest of you, I'm hoping that you're with me. I'm seeing numbers. Remember, you are at 0 degrees. Check your make sure you check your angle to be 0, 0. Because sometimes if you have used a simulator before, it might be at a different point. Okay? All right. All right. Now, the next thing I should be around 115, 113, or somewhere around there. You're going to put it like, try to put it like where the thickest part is. All right. Now, the next thing I want you to do is move the probe to B, and I want you to read the velocity for me at B. Okay? And make sure you write B and then write the velocity so I know I'm not still looking at the same one. Somebody's lost. Dreamer Scott, can you tell me what the problem is? Somebody is lost. I do not see velocity. If you look on the screen for a second, I have my green arrow. I should find a hand, maybe. A hand will do better. Where my hand is pointing, that's where the velocity is going to be. Now let me know if you find it. I'm lost. I don't know what I did. Okay, Elizabeth, can you show me what you've done? Okay. Oh, you got it. Okay, great. All right. So All right. So how do they compare? Somebody will write for me in the chat area. How do the two compare? Do not have probe won't move. Probe won't move. I don't know why. You got to push the probe. This little button right here. Move it to the left. It'll move the probe. And this button right here. Push it up. It'll move it up. They're very close. Very good, Joanna. The answers is a very minimal difference. All of you notice that it's almost the same. I mean, you might have maybe plus or minus 2, but they're pretty close. We all agree on that. All right? Great. All right, I'm going to take this one now and make sure everybody is with me on that. And then if you have any problems this time, just give me an X while we're going through. All right, the next thing that we're going to do now is, with that in mind, for those of you who were having a hard time, this is what you were supposed to have gotten with the probe at the lower point of the airfoil. It should have been around, I see 115, 112, depending on exactly where you put it. You're not going to be able to put it exactly the same place. And then wherever you put it on the top, it should be within plus or minus 2. And that should be that much of a difference. Now, when you work with your students, you're not going to give them the point A and B. I'm just doing that so we don't waste any time. You just tell them to find the thickest part of the airfoil and find the velocity below that and then the velocity directly above that. And that's how you come up with it's almost the same. All right? All right, cool. We're going to move on to the next thing. This time, we're going to change our angle now to 4.5 degrees. So go ahead and change your angle to 4.5 degrees, and I want you to tell me what the lift is. That way I'll know if you have it. Now remember, when you work with your students, you don't have, oh great, we got it. You don't have to tell them to go to 4.5 degrees. It just asks them to find a positive number. And the reason I did 4.5 is easier for me to check you guys, make sure we're on the same place. Great. I'm seeing 281. This is the first time I did this, and nobody's giving me in the lift in newtons. Sometimes other people do. But that's okay. If you want to use pounds, it's fine. If you're teaching newtons in your class, did you notice that you can actually change the pounds to newtons if that's what you want to do? The velocity also, you can change it to kilometers per minute if you want to, and not use miles per hour. So depending on what you're doing in your class, here's default with pounds. That's right, and so that's fine. I have answers for both. All right, so what we're going to do now is, at that angle, I want you to tell me what is the velocity at the bottom of the, at the lower part of the foil, and then on the top part of the airfoil, just like you did earlier. You're going to tell me the velocity at the lower part of the airfoil and then the top part of the airfoil. Okay, go ahead and write the two numbers for me once you have them. And, okay. All right, I'm seeing some numbers, so I know some people are with me, and I don't see any X's. Everybody's doing good, I'm hoping. Great. Somebody write me in the chat area, tell me which surface has a higher velocity. Let's see. Which surface has a higher velocity? The lower or the upper? The top. Great. All right. Oh, great. All right. All right. Great. We're doing good. All right. Now, this time, remember, I'm going to go back here so I won't confuse you. Remember how I told you to push the velocity button? This time I want you to push the pressure button as well, okay? Because what I want you to do is to tell me what is the pressure over on top of the airfoil and below the airfoil. Let's see if you can tell me what the pressure is. Or rather tell me which is higher pressure, the top, upper, or the lower airfoil. The top. Ooh, okay, the under has higher pressure. Okay, think about this. Okay. It's going to be pretty, the number's going to seem pretty close, but for pressure it is a little different. Okay, I'm giving a chance for those people who are getting where we want to be. The bottom will have higher. How does this relate to velocity? Can somebody put those two together? How does the pressure and velocity? How does the pressure relate to the velocity? As the pressure goes up, what happens to velocity? Faster moving air. Thank you, Megan. Lower pressure. All right. What do you know? What do we know about faster moving air and low pressure? There's a certain somebody that told us something about velocity. When velocity is higher, pressure is lower. Who can tell me who that person is? Ah, thank you, Michael. Give the guy the Bernoulli Award. Okay, great. All right. So as you can see, if you have been having a hard time trying to explain Bernoulli to your students, this is a great way to do that. Now, when you notice, if you had a hard time doing that, when you looked at the bottom, the velocity was lower and the velocity was higher when you were at an angle. All right, and just bear with me. There's a point to where I'm going right now. And then when you looked at the pressure, you notice the pressure was higher where? At the bottom, so you can push up, than it was on the top. Okay? All right, so whenever you had higher velocity, pressure was lower. And like somebody said, that's Bernoulli's principle. Now, a lot of you probably do a lot of Bernoulli principle demonstrations with your students, and if you have done all those demonstrations and you really want to show your students what's going on, that simulator is really good for that. I'm seeing an X with somebody. Let me see who is that. It has a red X. Do you have any problem? If you would write it in the chat for me. Ty, let me know what's going on. Oh, you said Bernoulli, okay. All right, now, for example, this is just my little granddaughter right here. We're doing one of the same experiment with a ping pong ball and a hair dryer. That's one way that you could do. Oh, still having Java problems. Oh, I'm sorry. And also the video from, there's a video where astronauts actually demonstrating Bernoulli on the ISS. That's where these two are coming from, so you can also watch that video. And this one is when you have a little ball in a funnel, and you blow air in a balloon, and actually you can tip it over, and the ball doesn't fall over. Some of you probably have done this. When you have two balloons and you blow in the middle, a lot of people think they're going to move apart. They actually come closer together. The water hose, you put in your thumb on there, increasing the pressure. What happens to velocity? Some of you have done that. The piece of paper, blowing across the piece of paper, and the paper flying up. Now, there's a great one that I've done with the younger kids. It's really cool. You put toilet paper roll and a stick in the middle, and you got to use one of those lip blowers. And that's a great demonstration for really the younger kids, and they can actually see the toilet paper actually rolling up, and that's really cool. So you could also try that one. But anyway, so that's a simple way with the simulator explaining Bernoulli's principle. Some of you probably have other ways that you can do the same explanation, but for your students to really understand it, actually seeing the airfoil, it does make a big difference. All right, and I'm going to move on with that one. So the next thing is, how is a boomerang like an airplane? Once you start talking about the shape of the airplane, we notice how it's an airfoil, and we also looked at the video. I mean, we also looked at the simulator and seeing what happens to the airfoil. Well, when they designed boomerangs, the boomerang also has airfoil shape. It has a leading edge and also has a trailing edge. And when you go back and look at a video about Gary, he actually, the guy that told us what a boomerang was, he also shows you what he does in his shop. He's actually designing a boomerang, and he actually shows you how he starts with a piece of wood and cutting it, and then how he shapes it into an airfoil. So when he's done, it ends up with a leading edge and a trailing edge, just like a regular boomerang, also just like a regular airfoil. So once again, once you continue with the video from the Boomerang champion that we saw earlier, you'll find out more about how to design real boomerangs. If you have students who are really getting into it, and you have one of those classes where, especially the technology classes, where they actually have these kind of tools, maybe they can use that. But that's not something we're recommending for you to use with students, but it just lets you know that it's there, and they designed the boomerang, so its shape is just like an airplane. All right, so Now, as you can see, your students will have fun with the boomerangs, but you also want them to learn something about it. Now, before we get into that, Paul, I'm going to give it to you so you can show them where the clip art is in case somebody missed. And I want them to tell me which one of these terms they might use to describe boomerang in flight.
I think you can, Rudo, and I would like to place your clip art into the table there in the area that next to where you think that the which one helps describe the boomerang in flight. And if you put your clip art items to the right of the phrases there, then we would appreciate that. And go ahead and do that now. And I have given you permission for your clip art. It is the 7th row of the tool column that is shown up next to your chat and participant window. And I see most people have caught on there, so I'm going to pass it back to you, Rudo.
All right, thank you. All right, it's still coming. All right, great. Now, you will probably find out something that you teach, and you will find some way to use the boomerang as a demonstration. Now, each one of those terms can be used, and these are just some. Some of you will probably find more. So studying how boomerangs work will introduce your students to several concepts of physics. And some of them are the ones that everybody should know, like Newton's laws of motion. So the focus of this lesson is really to encourage hands-on exploration of physics. You want your students to learn some of those laws of physics. You want them to know more about forces of flight. And like I said earlier, how far you go into it is going to depend on what you teach. For those of you who are math teachers, for the advanced students who want to explore the math and physics of flight, also boomerang theory includes the engineering of propellers and also lift created by the thin airfoils. So you can explain this, I guess, using the partial differential equations for those of you who are math people. Now, I'm not a math person. That's probably as much as I know about that. But so you can actually bring it to a lot of different things that you're teaching in your classes. Now, so for studying boomerangs, it sounds like something that is really complicated, but you can, like I said earlier, you can actually bring it down to a lot of different levels. So boomerangs have two motions that you want to think about when you think about how they work. Now, one, it rotates on its axis, and the other one, it travels along a nearly circular or maybe elliptical path in the air, and then it comes back to you. So what I did is I kind of gave you a simplified explanation of how a boomerang works. But I think this one kind of hits all the points that you need. So if you have older students, maybe physics students, you might want to get into more detail about that. Now, so the first thing I have on here, you're looking at our airfoil shape. So we're talking about lift. So the wings of a boomerang are set at a slight tilt, just like we saw in an airplane, and they have an airfoil design just like an airplane wing, which gives the boomerang lift. So remember, as we were talking about the Bernoulli's principle. So this is our aerodynamic lift. That's where that term comes in. So the boomerang is both moving forward and spinning, and also has two different speeds. More lift is being created on the upper half of the spin than you have on the lower part. Now, when you think about boomerang, greater speed means greater lift. And also, as it's moving like that, it does put on a twisting force, which we call torque, for those of you who teach that. So how the boomerang spins also depends on your moment of inertia. When you think about moment of inertia, is how easy or difficult it is to spin something. So your heavier boomerangs, they're going to travel with a larger radius. So if you think about doing your boomerangs in the class, in the building, you might want to think about smaller boomerangs. If you're going to be going outside, then it might be okay for you to do the larger boomerangs, okay? And then the next thing is the spin. So the boomerang is moving forward. Remember, it also is spinning. And also when you have that, when it's spinning like that, it's creating uneven lift. The rate of boomerang spin is determined by the length of the wings and also the angle at which they are joined. So your students are going to have to think about that when they do their designs. Also, the distribution of material and the amount of force that's being applied by the thrower. So if you want to have somebody being the test thrower, then you want to think about it. Do you want a lot of people to be able to do that? So when a boomerang is correctly thrown, it spins And from the time that you actually release the boomerang, it's going to start spinning. So spinning the boomerang causes the air to rapidly flow over the airfoils, creating lift, which is going to make your boomerang fly. All right, so the next thing is your precision. This is just like a gyroscope. A lot of you probably do demonstration with gyroscopes. You do that wheel demonstration, probably a lot of you physics teachers. So the uneven lift is being created by the spinning boomerang and making it turn. Now, it's going to keep on turning until it makes a circle and comes back to the thrower. So we're talking now about, I see Imani is putting on there gyroscopic precision. Very good. And so this is how we can, gyroscopic precision is how we maneuver satellites in space. For example, the Hubble Space Telescope. The gyroscopic precision gives the boomerang stability. So if you use gyroscopes as examples or use yo-yos, tops or in your classrooms, so that could be another example for that. So centripetal force is also used when you're explaining boomerangs, so because centripetal force gives the boomerang stability as well. So a boomerang has gyroscopic precision and also centripetal force, trying to keep it in a straight line. And in that position, aerodynamics makes the boomerang turn. And just like I'm saying, I was trying to use some of the terms that I have on the on that list earlier. But you can add your own terms depending on what level student you have and what you want to bring across. All right, and I'm going to stop there for a second, see if anybody has any questions. Now, I kind of went fast on the STEM connection because really it's going to depend on what you're teaching. I just wanted to give you an idea that you can pull out a lot of different things depending on what you want your student to have. And Paul, I'm not seeing any questions. If it's okay with you, I'm going to move on. Okay. All right. All right, cool. So the next thing is, now that we know something about a simulator, oh, I forgot to tell you not to get rid of the simulator. I'm hoping that you still have it. If not, go ahead and click back on the simulator. If you lost it, here it is. Sorry, I meant to remember to do that. There is a misconception that a lot of students have about lift. And I used to tell people, even when I was trying to learn how to fly, my ground instructor also had this explanation wrong. And I would like make sure that if you teach anything with flight, make sure this is the one thing that people understand. Now go ahead and click again on the simulator for me. I did put the link back in the chat. It should pop up right away for you this time around. Now what we're going to do now is we're going to look at the common misconception that most people have. A lot of people believe that when air is moving, the air on the top, we know it does move faster, and a lot of people think because he has a longer way to travel, he has to move faster to catch up with the air that's moving at the bottom of the airfoil. So one of the things that we want to let you know is air does not play catch up. From the experiments that have been done in the wind tunnels, they've shown us that. And so we're going to quickly go back and try to look at that. Now go back to your simulator. This time, you're going to push the directions button. Okay? You don't need to worry about anything else. Make sure you push in your directions button. We did not have that earlier. And also, I want you to push the far view button. Okay? And we're going to leave our angle at 0. No, we're going to change our angle to 4.5, sorry. Change your angle to 4.5. We want it in an angle. And I've added something else. The airflow is the button at the bottom. Once you look on within the yellow. So if you have all of this, if you give me a green check, then I know we're ready. I'm going to clear this. If you have done what I just told you, give me a green check. Great. We want directions. We want far view. We want angle to be 4.5. Okay? And you need to know where your airflow button is. Okay, now what we're going to do for this one, let me see, I think I did another picture for you. Here we go. So this is what we're going to be doing. The angle is going to be 4.5, and I want you to look at the front of the airfoil. You have, again, I have an A and B, which are not on your simulator, but I put them here so you know what I'm talking about. Now, A is pointing at this yellow line right there, and B is pointing at this little yellow line right there, okay? So the idea is to keep your eye on that yellow line all the way as it moves to the back of the airfoil. We want to see if the B and A will get to this tip at the end of the airfoil at the same time. And how you move the airfoil, where it says the rake release, that's where you push it to your right. Okay? I'm hoping that's clear. With your students, remember you're going to have more time. Don't forget to push your directions and far view. Airflow button is going to be this rake release, David. Okay? If you have it, let's get started. Push the directions button. Change the angle to 4.5. Move the yellow particle from A and B all the way to the rear, and the way you do that is pushing this little blue button where it says rake release. You don't need the probe this time. You don't need to worry about the probe. My point is, do they get to the tip at the same time? I see Michael has it already. It is moving faster, but a lot of people think it's moving faster to catch up, Elizabeth. But the idea is they do not get at the tip at the same time. And that's what we're trying to get to your students. We know it's moving faster from the experiment that we did earlier. So let me see. I'm seeing answers in the chat, and they're correct. I'm hoping everybody's with me. So once you move the particle to A and B, you find out that, yeah, B is going to pass the finishing line before A does. So there is no catching up. So if you ever somewhere somebody's explaining moves faster so it can catch up with the slower from the shorter path, that is not correct. So this is another good way to explain that misconception, because a lot of students have misconceptions on that, and I've heard a lot of even adults explaining the airfoil and how air moves the same way. So you might want to play around with this a little bit and talk to your students about it and let them play around with it and then ask the questions. I know I just kind of give you everything in a short period of time. So hopefully you got something out of it, and the idea was to just get you started. So once again, this is a good way to explain that misconception about how air particles move over the wing and under the wing. Now that you know a little bit about that, then you have something to share with the students. Great. All right, so this is it. Now there is also another simulator that is recommended in the guide. Now this one is more about other things. For your more advanced students, as you can see, things change. You got camber differences, you got Reynolds numbers, and you got other things that you're comparing, lift and drag. So if you're really getting into those kind of things, then this is something different that you can use with your students. It is also recommended for you to use, but it's another way to explain. Now, just for you to remember, this simulator is not a reality. It is just an educational computer program. So it's just designed to help your students understand what's going on. All right. And that's all we have. And with that, I'm going to hold for the question to the end. Kind of took a little longer on some parts than I thought I would. But anyway, one of the things that we want you to do is for you to share with us on Facebook. And also, if you're not familiar with NASA Explorer Schools, go ahead and click on Explorer Schools at nasa.gov. You'll be able to find out more about what we do at NASA. And the Facebook link, I am going to put it on there while you guys are doing the survey for Paul. And once you go to explorerschools.nasa.gov, you're going to find where it says register. And then once you register, you're going to be able to find the lesson that we just went over today. So you go to the lesson library, And when I was telling you earlier, all the PDF that you need, materials, are all on here for you. And also, those who are NASA Expert Schools educators, do not forget to do the survey with a green check. If you do this lesson with your students, do the survey with a blue check, okay? If you want to see all the videos I was telling you about, if you click on the video camera, it's going to take you to a video collection. And as you can see, there are a lot more videos that I did not show you. You got like 3 pages of those that I did not share with you today. So you need to go there and check those. And they're really, really good. A lot of them will give you a lot more information on how to ask questions to your students about what's going on. And for those of you who are not familiar with NASA Expert Schools, we have school recognition for educators and teacher recognition. I think our teachers find out today who will be going to what summer workshop. And during the summer, we actually will be taking students to, not the summer, but in the first week of May to Houston for our student recognition. So hopefully you guys had a lot of fun with it. When I started giving this assignment, I did not know much about boomerangs. But I have a friend in Australia, so I had him send me boomerangs. Like I got a whole box now of boomerangs. Oh, there's so many kinds and different designs. They're really, really cool. So hopefully your students will have a lot of fun learning about boomerangs. And I'm going to put the link for our Facebook in the chat area while you're doing the survey for Paul. And then I want you to share with me what you do if you have pictures from your students. And this is the Expert Schools website. And Paul, with that in mind, I'm going to give it to you, and I want to thank everybody for joining us tonight.
Thank you, Rudo, and please a round of applause for tonight's presenter and fantastic program and information as well. I was happy to see this program for the first time myself and learn quite a bit about boomerangs as well. So thank you again, Rudo. Thanks also to NASA for sponsoring tonight's program. I'd like to remind you to join us in the Learning Center and take advantage of the over 7,000 EPD resources for your development, as well as register for future web seminars, and also join us on our community forums. I'd like to thank the administration of the National Science Teachers Association for their support for web seminars. And I'd like to bring your attention to the upcoming programs that we have tomorrow. Designing Effective Science Instruction. On Monday of next week, we have the National Science Foundation sponsored Exploring Beneath the Antarctic Ice with Waves, Finding a Lake and a Passage to the Ocean. And finally, back on April 18th with another NASA Explorer School program, Algebraic Equations, Calculator-Controlled Robots. If you're watching this program on an archive, we hope to see you soon on a live web seminar.